Jake Sioka. I'll be explaining how to use Ansys-Fluent to analyze a cylinder in a wind tunnel. Now, we already created our wind tunnel in the last part, so we're just going to copy and paste or duplicate our previous geometry, and that'll give you this new one. And then we will open up our duplicated geometry and add the cylinder inside. Once it's loaded, you won't have the cylinder yet, but you'll have to come to your Sketch 2 and create or calculate the distance to be in the center of your test section from 0, 0, given whatever reference values. And you're going to create a cylinder at that point. And once you do that, you can create concept from sketches or surface from sketch and generate it. And that's all that you're doing different for here. And then we can open our mesh. Now, very similar to our first part, we're going to name everything. Exact same names for your inlet, outlet, and walls, but you also want to create a cylinder name. And once that's done, we can start same meshes with our method mesh, but set to triangles over the whole body. And then we're going to do edge sizing. So you will insert your sizing mesh, but we're going to select our inner cylinder edge, and we're doing number of divisions. I set it to 100 divisions, and no curvature, and your behavior is hard. And then you're going to insert also an inflation mesh also around your cylinder. So your first geometry face will be your body, and then you also select the circle edge. I did a smooth transition of 0.1, 200 layers, and then no growth rate, so set to 1. The last part that you want to update is your element size of the main mesh. I just chose this value, and that'll change all these tiny triangles, make them smaller throughout the entire mesh. And then here's your inflation mesh, and then as you get closer, you can see that it gets finer and finer towards the edge of the cylinder. Once that's all done, you can generate your mesh, update it, and open your setup. Again, 4 solver processes and double precision. Now that setup's loaded and you have your cylinder inside of your test section, we'll update our model to be turbulent, K-epsilon, keep this standard. You can do standard wall function or enhanced wall treatment. If you do enhanced wall treatment, you want to make sure pressure gradient effects are on. Then we can double check our fluid and our air is set to the same values as given. Next, we will update our boundary conditions, make sure it's a velocity inlet 5.625 velocity at your inlet here, but because it's a contraction section and we want 15 meters per second through the test section, this is the value I found. And then double check your outlet's a pressure outlet, which it is. All that looks right, so you come to your reference values, make sure everything updates, double check your residuals. I set mine to the -5, and then you're good to initialize and calculate. And I did 500 iterations, which we can cut back to when it has flattened. Now that my residuals have flattened, I'm just going to stop it early, save some time, and now we can get into the contours and graphs needed. We only need a velocity and pressure contour, so I'm going to leave that for our results tab, but in order to get our pressure coefficient, we're going to need our static pressure data. because it won't be accurate through Fluent because it'll be taking your inlet velocity, which is 5.625, but you actually need to use your 15 meters per second velocity. So here we're going to do our static pressure over our cylinder. Looks like this, which is good. Deep drop and then it flattens. And you can write the file and save this, export it into Excel, and then do the required calculations in there using atmospheric pressure and whatnot. We also need our drag coefficient, which you'll need to get your drag force because, again, for the same reason as your pressure coefficient, it'll use your inlet velocity. But in order to get your drag force, you're going to do new, and then force report over your drag, and choose drag force along your cylinder, and compute, and you'll have to save this value, and then do the calculation in Excel or on your just a paper to get your drag coefficient. That's all we need from here in part B. So we'll go ahead and open our results tab to do the contours. Now that we're in here, we're going to create contours using the contour button. First one we can do is a pressure contour. You want it through your symmetry 1 as a pressure variable, and then 110 contours. It'll look something like this. We have low pressure at your high velocity points, so edges of your contraction zone, and then high pressure at low velocity points, so you kind of have a stagnation point here, and lower pressures on the top and bottom of the cylinder. If you do the same for your velocity contour but update the variable, you can see that it's the opposite, and you have high velocity on the top and bottom, and then it's again stagnation point and your wake zone. High velocity around your contraction edge, and you can see as it diffuses. And that's everything for part B.